All right, let's get started. So we're going to start a brand new topic today on nonparametric approaches to graphical models. This is one of these areas I actually knew less than my students do. So you can see the slides was actually prepared by Anchor Parak over the years. And now I made some modification. In case I got stuck in some places, don't blame me. We're going to go together and ask Anchor about that. So it's a very new area in graphical models, which actually is still less understood than the rest of the material we covered so far. Okay. It's less understood in a sense that people are still trying to figure out what kind of advantage in practice that this new approach can give us. Although in theory people understand very well there are good potentials, but in practice there are still a lot of space for people to understand. And part of the problem of this gap is because not too many people are practicing this new approach or even understand this new approach. So the purpose of including these 3 lectures in this class maybe is the only place in the nation that you can see this kind of stuff in the class, is to encourage you guys to look into it and hopefully find good use cases for that. I'm going to talk about a use case next week on a natural language processing problem called parsing. But I think there are other applications in time series data analysis, in language modeling, and you definitely are welcome to explore more of that. So it is to basically allow you to do this. You are going to have a complete graphic model for which you don't like to use a parametric assumption, meaning that I don't want to make assumption on Gaussian or multinomial or stuff like that. I have this weird shape that is very hard to describe parametrically. But I'm going to deal with inference and learning problem of this model by not explicitly making any parametric assumption. Instead, I'm going to make a projection, of this whole thing, the distribution itself, into some other space where, all the probabilistic inference and learning operations, such as marginalization, conditioning, and so on, can be actually realized by some linear operation, and which actually implicitly, are working on high-dimensional nonparametric models in the original space. But in this space, they are just the linear operations. And we're going to find out how to achieve this mapping, what to be matched, and so on and so forth. So it's a pretty, less intuitive way of understanding graphic models. It needs actually a lot of preparational knowledge. And today we're going to start with one of this knowledge known as the Hilbert space embedding. You probably heard about that a little bit before, right? In SVM, you probably heard the benefit or the, what is really magic about SVM is this trick where the data can stay in an infinite dimensional space, right? And everything that is complicated in the lower dimensional space gets now unfolded and become a linear separator in the infinite dimensional space. But then you don't have to deal with the infinity because you have kernel trick and all that. So we're going to repeat and review these kind of materials here, but we're going to go one step further, in which the earlier technology was telling you how to embed a point into an infinite dimensional space. And here we're going to talk about how to embed a whole distribution into such a space. So that's kind of the high-level message. All right, so why we do that? I think I kind of delivered that already, but here is a very high-level summarization. So basically, there are different views, operational views of graphical models. And what we've been experiencing so far is this so-called optimization view, right? You write down the graphical model or any distribution in a explicit form with parameters, with everything. And then the problem of doing inference and learning is really about solving an optimization problem, right? In the most authentic case, you solve a maximum likelihood estimation, or if you have other different ways of relating this to other loss functions such as a maximum a posterior probability, maximum entropy, and later on we're going to talk about even jointly maximum entropy and maximum margin and stuff like that. You are solving a optimization problem in the space of all proper distribution. Okay, and the space can be also defined in a flexible way. Right now we are dealing with the space of all proper distribution, right? Everything that normalized to 1. But we already actually see a few other places where the space can be more flexibly defined. Remember the mean field approximation and the best free approximation, right? We're talking about a outer space and the inner space of the marginal polytope, which is a subspace or superspace of the distribution, right? So that's the advantage of optimization. Everything is very explicit. You can express the loss, the space, in closed form or in analytic form, and then that allows you to derive principled ways of approaching that, including approximations if you knew it is too hard, and then you can even use many existing methods such as a fixed point iteration, message passing coordinate descent, stuff like that, to approximate or exactly solve that optimization problem. But the real limitation of those is actually unavoidable. It is starting from the very beginning that you have to make a assumption of the distribution. And what if you have a non-Gaussian continuous variable and you have a non-convexity, for example? And what we do right now is to ignore this case. We basically ignore anything that's non-Gaussian, right? Since it is Gaussian. And for non-convexity, we say let's hack around it. Right? Maybe the EM algorithm is a way to hack around it. You basically impute the latent variable, make them biconvex, and then fixing the parameter, you can get the estimation of the hidden variable. And the hidden variable, once they are estimated, fix them. And then you estimate the parameter, which is now another convex problem, but it's a biconvex problem. Overall, it is still non-convex. You get this kind of hack and the heuristics. And the other view that I'm going to try delivering today, I'm not sure whether you can really get it back after 3 lectures, is this linear algebraic view of graphical models. And in that view, the focus is on operation, not on objective. Okay, we don't actually explicitly write down a loss function or anything. We just want to make a translation of the stuff you do in the probabilistic space into a linear algebraic space, and claiming that they are really doing the same thing. And then we're going to argue that doing there, once you have the kernel trick, you have everything like that, you can do it in a bigger space of possible distributions, namely nonparametric space. And it gives you a number of, how should I say that, maybe a modeling advantage in modeling power, especially you don't have to make this Gaussian or non-Gaussian assumption. Okay, you basically let the data to define by itself what distribution you need to handle, right? Remember, I guess most of you probably know what is a Poisson density estimator, right? And in there, you don't make any assumption. You basically use a bump, to define over the data points. Then the density of the entire data set is defined by summing together all these data-centric bumps. But the flexibility that is, you don't have to make any assumption on the overall distribution. So that's one obvious advantage. The other less obvious advantage is that because of this linear algebraic operation and the view of the inference and learning problem, sometimes you don't have to experience this local minimum free issue. Okay, after some proper transformation, you can get a solution which is local optimum free. Okay, and through some linear algebraic operations, you don't get exactly what you get in the optimization space, but it is a transformation that is deterministic. And also, it gives you different theoretical perspective, And also a cool thing it is now you see a grand unification of graphic models, kernel machines, and stuff like that. That's, of course, intellectually quite interesting. All right, so that's basically the motivation, and let's see how we're going to start. First, obviously, I don't need to convince you too much. There are nonparametric, non-Gaussian distributions that we need to care about, right? So here is an example where if you want to model the depth of an image, and you need to basically carve out a location here. If there is a depth difference in this small region, then for sure the distribution of whatever features or elements inside that shouldn't be Gaussian, right? Because Gaussian is a symmetric distribution, which kind of tells you there isn't any depth. It should be a random kind of distribution. And then on real data, the data you collect from different places, you see also weird distributions, right? So this is the demographic of men and women in Canada. And you can see that the peak is people a little bit older than me, okay, in the late 40s. And then you see this a tail here, and also a heavy tail here, a light tail here. Okay, so a pattern for the developed country. Then here I have another populational distribution for Afghanistan. Okay, and you can see a sharp difference, right? So the biggest population are these newborns, the babies. It's actually quite common for both boys and girls. And then when you get older, the population is smaller, probably indicating a nutrition or health or other risk in their life. So how to model that? It is obviously not a Gaussian, right? So these are basically arguing for the needs of really non-Gaussian entity in many of the real graphical models. So now let's see what graphical models can offer us. Right? So this is a graphical model. It offers the biggest advantage is that this graph you can now systematically synthesize multivariate distributions by multiplying components. But on every component, you don't have much choices. Right? We talked about a few. For example, this is a binary distribution, and this is a conditional binary distribution. You can make them probably multi-way, like using a multinomial, or you can maybe make them continuous. But once it's continuous, it's usually a Gaussian. Okay. And then once you set up that, you need to learn a parameter, and then you actually already knew what parameter you are going to learn. It is a parametric model. Then you are going to collect sufficient statistics, right? Which basically means counts or conditional counts. And then they will be translated into the frequency or probabilities in each of these entries. And inference, of course, we also know that. Graphical model is maybe another biggest advantage of graphical model is that inference is made easy. Right? You can do operations according to the graph topology and run exact inference algorithms such as variable elimination, PD propagation, or if the graph gets too big, you have loopy BP, mean field, so on and so forth. So that's basically all what you get from a GM. Now, back to this issue. What if I have something like this? Okay, maybe I already know that. Empirically, I know that A follows this distribution, which I really don't know how to parameterize. And then maybe in here, one of the nodes in here is this one, a bimodal. So how do you write down a conditional probability of this guy given that guy? Okay, linear Gaussian or mixture model, or you name it. It probably does not give you anything, right? You just cannot really, prescribe a mode and you cast iron something into that, right? All right, and as a consequence of that, you don't know what to learn because what are these parameters is unclear. Right? And inference, of course, is out of the question because you don't have really the vehicle to define the loss function or the target for you to derive. All right, so when in the good old days, when people run into this problem, this kind of weird distribution, of course, one way is to discretize the data. You bin it, right? You bin them in 4 ways, and then you basically say whatever falling into this bin to be 0, and so on. Okay, that's a way of discretizing data. People do that all the time. But in these cases, a lot of information is lost. Not only this subtlety in the curve, in the curvature is lost, but also even the meaning of the data can be lost. So here you have a 3, and you have a 2, you have a 0. And to a proper distribution defined on this 4-way discrete distribution, in fact, all numbers are equal, right? There isn't a difference between 3 and 4 or 0. They are just the options of discrete outcomes. And you write down a multinomial, and your inference will be assuming that each of the entity is just one of the many possible options. There isn't a way for you to express knowledges like 3 is closer to 2 than it close to 0, and so on and so forth, right? So this is not a good idea. So a couple of years ago, it's actually been a few years, a bunch of folks, as I listed here, Fukumitsu, he is in Japan, Bernard Shokov is in Germany, and the rest either are here or was here, as postdocs or as faculty. And they actually started this new trend or new direction of formulating probabilistic modeling with continuous variable using kernel techniques. Have a question?
Yeah, I have a question about the last slide. How is this different than a histogram? And because like in a histogram, you're still keeping an ordering.
It depends on how you model how you represent the histogram. If you want to use the histogram to do inference, right? And you place them into the bin, and you get a probability. That is fine. But if I have a multivariate distribution where these different dimensions, different directions can be actually related, or maybe that's not a good. Yeah. So even in histogram, for example, it's hard to do inference on histogram, right? When how do you write down, for example, a conditional distribution conditioning on a histogram? That's actually another complications, right? So, I don't have additional story to elaborate on that, but I think people see it. Right? This is a solution that even for histogram, for example, you probably can do it on 1 dimension, but I have a multi-dimensional distribution, you cannot do it either, right? So yeah, one can fix it to serve a certain needs, but you really cannot express a lot of semantics in a model. Okay. For example, if I do it using some other transformation, you actually can do a mapping of the points from here into a infinite dimensional space where the distances can be made available. And you probably don't even know what I can make out of it. Why? Because it's never made available, so people even didn't think about how to make use of that information yet. But now I tell you that you have a point which was originally 1, and now you have a second point which is 2, and a third point which is 3. And knowing that you have this kind of property, your inference procedure might be different than just looking into a histogram. Right? So that's a potential possibility. The way you index the different bins, if you have a lot of histogram, the way you search it, do you do a uniform search, or do you actually do a distance-dependent search? That will be all very interesting. That's why I say now exposing to you this kind of advantage, hopefully, you should actually start thinking about what kind of a new capability or inference you can perform, okay, with a new representation. Anyway, so I had a very good luck in working with one of these guys, Li Sang, who was a postdoc in my group. I got to learn a lot from him. And Arthur Gretchen was a postdoc with Carlos a few years ago. They actually overlapped, and then now Alex is here. And we have actually a strong local presence of this whole direction of research. So if you didn't get answer from me, you should go look for those other people here. Okay, so first, the current status is that people like Gaussian and like a parametric graph model for obvious reason, right? So I think this very parametric assumption makes things simple. There is a easy bijection between a distribution and a set of a small number of parameters, and therefore you get a lot of saving in representation. And also operation on Gaussian can be easy. We learned, for example, how to deal with marginalization conditioning on Gaussian, right? Conditional distribution under Gaussian is itself a Gaussian, and the conditional mean and the conditional covariance is that subvector and subblock in the original covariance matrix, and so on and so forth. Then we have matrix inversion lemma, all that kind of tricks to allow you doing closed form conditional inference. Right? So these are all good for Gaussian, but again, if you are in this domain, you really cannot benefit from a Gaussian assumption because the data isn't Gaussian. So let's try to now find out maybe a different way of expressing this fancier distribution. So in Gaussian, basically, we used two numbers to represent distribution, right? Which is one of these is the mean, right? And so we can also represent this with the mean, right? Why not? Okay, and why it is not a good idea? Well, for Gaussian, maybe the mean tells you something because it's symmetric. Therefore, it tells you a mode in the data. But here, if I have a arbitrary multimodal distribution, that mean isn't very informative. I lost a lot of information. Okay, so no good idea. Well, how about I put the second order moment into there? That basically is all Gaussian distribution is about. They explicitly, completely capture the Gaussian distribution. In our case, because we at least have two Gaussians, if not non-Gaussian, and this one is not going to be sufficient. But it's better than here, right? It captures something. The spread of the data is somehow incorporated. Maybe you are still not happy. How about this? We have the third order moment of that, right? And okay, I think people will agree this will be even better if we can compute it. Okay, if we knew how to compute this, it would be better. But still, you lose something. How about we just go on and infinity? Okay, you can imagine that if I go infinity, this whole thing will be captured. Why? Because this projection is up to you. I can be as stupid as remembering every point in here and put it there. That's my infinity, right? If I don't have a resource limit, I can remember everything, right? So that's the intuition. You probably can be convinced that a high-dimensional vector, maybe conceptually infinite dimensional, can actually be used to describe a distribution. So there is a possibility of a mapping between a distribution and a vector in some space, right? So that's basically my first thing. You can maybe imagine I can have an interpolation in here, very, very dense one, and put something there as well. So that's basically, the first insight. There could be a information lossless mapping from the distribution to a vector in some space. And the difficulty is that if this is infinite dimensional, how am I going to deal with that? How do I manipulate? Right. So for that, we probably can instantly react with at least some buzzword. Right. This kernel trick is something we knew to be good with infinite dimensional models, because with kernel you never need to really touch an infinite dimensional vector, right? As long as your sets of operations on those vectors are defined a priori. It doesn't allow you arbitrary manipulation, but if you manipulate them with only dot product or something, then I don't need to maintain the infinite dimensional vector itself. And that's basically motivated by this SVM problem, right? SVM is about minimizing a hinge loss, and here are the margin constraints, right? And now we can basically the nonlinear kernel SVM is about imagining my data points now gets projected into an infinite dimensional space by a phi alpha, and my weight W is also infinite dimensional, right? Although here I'm just writing them symbolically. In reality, you never get this to infinite dimensional, right? So in this primal SVM, at least operationally, you cannot do infinite dimensional mapping. But we knew that if we do a dual formulation, then this whole thing is equivalent to this one, okay, the dual problem, and in which you can see all these infinite dimensional vectors never appeared alone. They always appear in pair, not only in pair, but in inner products, right? So here you have a pair of transformed data, and I think that's it. And if you are talking about a division boundary, it is going to be, anybody remember what is the division boundary of SVM? It is WT times phi of xi, right? And we are asked whether it is greater or smaller than 0 or something, right? But what is W? W is basically a weighted combination of some support vectors, right? So it will be alpha j times phi of xj, right? And I'm going to have a collection of that. J equals to my SV support vector sets, right? And then, this whole thing translates to now, this inner product of this guy times my testing data point xi. Therefore, you again see, the transformed data to be always present in the form of a pair, right? Okay, so then, the kernel trick says that you are going to now, replace this whole thing with some kernel function. And that makes basically an implicit, operation in the infinite dimensional space without even dealing with the infinite dimensional vector. All right, so that's the kind of the kernel trick, very, very clever. And now we ask, can we use this to deal with our distributional embedding? All right. So that brings us to this embedding idea in the Hilbert space. So Hilbert space is basically this nice space where you have a lot of linear algebraic operation properties, which I'm going to enlist in a second. And also mapping means that you need to have a one-to-one, correspondence between your original entity to the mapped ones. And then, even though the statistic can be infinite, in the transformed space, we can probably cleverly construct some kind of kernel trick to make them more clickable. Okay? And in particular, in the later lectures, we're going to show you that this idea can even support things other than inner product. It can be applied to Belief propagation and other fancy operations that we use in statistical inference. Okay. And we're going to first introduce the Hilbert space concept and then build operators on that. These operators correspond to actually the fancy statistical inference that we're going to address. So again, Hilbert space is a vector space, and a vector space has this property. Okay, it must be closed under linear combination. Okay, and here I have V and W, and here I've been explicit about what is V and W. Okay, you can take them as two very long vectors. Okay, and then this is a linear combination of two vectors, but they can also be a function. Okay, that is implicit. That maps you from the one space to the other space. So this law says that the linear combination of two objects in the space still puts you back into that space. Okay, and so this is an insight. I want you to be a little bit, abstract, metaphysical, so that you can use the the intuition in linear algebra to hopefully understand what's going on, but hopefully you can go beyond that and understand its potential in a bigger way. So these two things can be kind of viewed as a vector, but now I ask you to view this vector as a infinite dimensional one. Okay, and the infinite dimensional vector, sometimes we call it a function. Okay, the function basically says that I have a space of I have a point x, which is in my feature space, original feature space. Now through a function, I get it into maybe a point in here, which is really infinite dimensional, and this mapping is called f, just like the phi we see before. So yeah, so an infinite vector in the vector space corresponds to a transformation function. Okay, note this one-to-one equivalence. And then what is a Hilbert space? Well, a Hilbert space is a complete vector space equipped with the following linear algebra operations. Right? So you are familiar with all this already. It should be equipped with this inner product operation. The inner product has the following character. It's symmetric. It is linear. It is non-negative. It has the zero property. Okay, and this is just as if you are dealing with a finite dimensional Euclidean space. Okay, but it's called Hilbert space now because it can go infinite dimensional and it can be now denoted by the function f and g rather than give you a long vector of numbers. Okay, and so this is a so-called a nice infinite space, and things behave almost like they are in the infinite space. Okay, but only symbolically. Okay, the actual event happens during this dot product can be very, very different from the finite dimensional space, but they look like what they have in the infinite space. And you can still use notions like a norm, there's orthogonality and stuff like that to characterize the property of that space. But operationally, they can be different. And here is an example. For example, in the Hilbert space, the inner product is now defined as the integral of these two corresponding functions, right? And you can probably see this abstract picture, right? Imagine, this one f is one of this vector, and that one g is one of this other vector. If they are infinite dimensional, then they basically collapse on top of each other and have a sum, which is exactly what you do in the integral, right? The integral is to add together, a valuation of the function in that infinitesimal space, and then sum all of them together, right? Okay, so that's basically a ability I want you to acquire, to somehow build the connection between finite dimensional linear algebra to the Hilbert space operation, which is infinite dimensional, but sometimes we just don't mention the word infinite dimensional. It is really an integral between two functions. Okay, although geometrically they look like a dot product in infinite dimensional space. All right, so this is a operator called the inner product. We can have other operators, right? So here we define a operator C, and here we say in the Hilbert space language, we say operator C is mapping a function f in one Hilbert space to another function g in another Hilbert space. These two Hilbert spaces are different. They are both infinite dimensional, but they are of different dimensionality if you are using the finite dimensional language. Okay? And so we write it like this. This is very much like what we do in the linear algebra, right? You basically left multiply a vector with a matrix, and the matrix, if it is rectangle, then you map from a dimension m to dimension n, right? And they are two different dimensions. In here, we say the two spaces are different. We don't explicitly say the dimension. They are all implicitly infinite. Okay. And therefore, this C is basically just a operator. And this operator has this linearity property. Okay.
Can you characterize one infinite Hilbert space from another? For example, in the finite case, the space is defined by the basis vectors. Is there something equivalent in the infinite space?
In fact, this infinite idea is not necessary if it is further confusing you, because we basically don't want to explicitly try to map the thing to the infinite space and say this is a feature 1, feature 2, up to infinite features. That's actually not helpful. We're just going to say there is a capacity out there to expand the whole model. But what's really that you remember is this algebraic operator. Okay, it is truly just an algebraic operator to a transformation. You can imagine this is a transformation of a function. That's it. It could be a integral of one of the components and then map them to a different function. And these two functions does not even are not even defined implicitly with explicitly with dimensions. Okay, yeah, just view this as a functional transformation. And equivalently, we have the adjoints, which satisfy this property. Again, it is a very abstract. It basically says that any function, okay, is called an adjoint of this operator if it has this property. Okay, the transformation to f inner product with G is equivalent to the adjoint transforming G inner product with F. Okay, and this is like the transpose or conjugate transpose in linear algebra. Okay, and what that is, let's not worry about this at this point. It is just a function that hopefully we're going to use later on to perform some useful operations. And then the other operation is called the outer product. Outer product is also very mysterious, right? And in linear algebra, we know what is outer product, right? It is basically a matrix vector operation in this way, right? It's the reverse where you are going to use two vectors to create a matrix. But in the Hilbert space, it actually translates to a function which has this property. If you have the outer product between f and g, then they can be redistributed. And when this, with this operator, okay, applied to an argument h, they have this redistribution property that the first one can be moved on to the end. The second one can be inner producted with this one and scale up the other one. It's just a totally algebraic preservation. And again, we have the vector space equivalent to that. The outer product operation in vector space satisfies this property. Okay, so in here we just define such a function that satisfies this property to be the outer product of two functions. So yeah, so now we're talking about outer product of two functions, not the outer product of two vectors. And okay, so now we are about having all the definitions of operations. And let's resort to one particular characterization of the Hilbert space, which is something we want to stick to down the road, okay, in performing our transformation. This is not any Hilbert space, okay. It is a Hilbert space with this reproducing property called the reproducing kernel Hilbert space. And to understand that, one more concept, which is called this Mercer kernel. Mercer kernel is a kernel function of two arguments, which has this nice symmetric property in the sense that if you do this operation, okay, you get a positive number all the time. Okay, and here you can imagine there are all sorts of f you can use, all sorts of k you can use, but as long as this property is satisfied, then k is called a Mercer kernel. And again, it is roughly corresponding to a positive definite matrix in our linear algebra, right? Okay, so this is something we're going to make use of. The Mercer kernel is the kind of kernel we're going to use to build our transformation, okay? And many other kernels map you from here to here, but they may be a little bit harder to characterize, and we're not going to use that. So here are some examples of this kind of Mercer kernel. One is the Gaussian RBF kernel, which we often use. And there are polymer kernels and other things. Right? And so you can see this Mercer kernel had two arguments. Okay? And it's basically a symmetric operation to evaluate a scalar, a pair of arguments into a scalar. Okay? And sometimes you may be willing to call it a distance or whatever, but here that's not the point. We're just talking about an algebraic operation, turning two input into a scalar. And what if I make them into a transformation function? So here you are not really transforming a vector. You can call them transforming two vectors, right? Two inputs. But when we talk about transformation function, we often talk about transformation of one input, right? So what we do is going to take one out of them out. Or maybe I should do the other way around. what if I bring the y out and make this one a known thing, or maybe an index of this function? I'm going to always stick to y without change. Then I'm going to apply this to all the possible x that I can run into. Then we effectively turn this kernel into maybe a function like this, right? Because the argument y is now used as a constant index, okay, which you can call it an intrinsic parameter of the function. It doesn't matter. It is given a priori. And this one is not given. It is going to take arbitrary input down the road. And we call this a feature function, okay? And a feature function is basically the fundamental building blocks of what we call the reproducing kernel Hilbert space, okay, the RKHS. It has the very interesting property called the reproducing property, which we'll be seeing in the next slides. And here again, the reproducing this feature map has a asymmetric treatment, at least symbolically, of the two arguments, and the one now become index. And they, if you have a number of anchor points that you want to use to instantiate this kind of mapping function, then you get a feature map. These are a feature map of two such features, right? This is taken x to be 1, this take x to be 0.5, then y in this case is a free argument. Okay? All right. So now define inner product. Inner product is in this case, in this particular type of kernel had this interesting property. If you are talking about these two feature functions, these are two features, right? One is mapped on anchored on x, the other is anchored on y. Then they basically can be represented by this half kernel, basically, two half kernel. But when they go together, they actually correspond to the kernel evaluated at the 2 points. Okay, so that's basically the definition of the inner product for the features. Okay, and therefore this one corresponds to a feature function here, and that one corresponds to a feature function here. But now this dot product of the two features is actually gets you back to this full kernel with the two value in place. Okay, it's not an arbitrary scalar anymore. And therefore, you can also write this operation in some other way. You can basically say that here there is a deep connection between the Mercer kernel and the projection and the feature values. So this is a feature function, okay, with feature x, okay, and therefore it defines a function to project y. But once you project that, it gets you an evaluation of the kernel itself at x and y. And vice versa, here you have a feature function with feature y, but evaluated at x, it also gets you an evaluation of the kernel function itself. Right? So that's basically the nice thing about the Mercer kernel. Remember, Mercer kernel is kind of a symmetric thing. Now it gives you the advantage of establishing correspondence between the mapping and also the anchor point that defines the feature function. And those translates to an important property known as the reproducing property in here. So here I'm going to define a space, okay, of functions. And this is a set of functions and which can be expressed by linear combinations of feature functions. Okay, and the set F0 is the set of all such functions. Okay, and we call this a reproducing kernel Hilbert space. Okay, it corresponds to the completion of F, meaning that these little holes in the middle gets all filled up. Okay, basically in this space you have all the functions having this feature. They themselves can be built on linear combinations of bases, and they have a very important property called the reproducing property, which is in here. Suppose that now you want to evaluate an arbitrary function f. Okay, you want to evaluate that, and that basically is corresponding to a linear combination okay, of this function, okay, in the in the reproducing kernel space, okay, with the basis function, anchored at that point. So this is the proof. Now you have a y, which is a arbitrary function in the RKHS space. Therefore, it is satisfying this definition. It can be expanded, okay, with the set of feature functions. This is the feature map. And then I'm going to now introduce this mapping, this mapping phi of x, which is the map of the original point, okay, into my my RHS space. And then the dot product between this and that is now written in this form. And the alphas are the constants of every feature, the weights of every feature in the map. Take it out, and we have something in here. This is the inner product between a feature at xj and a feature at x, right? And this is due to linearity of the inner product. And then we go back to the definition of the kernel, right? And that basically gets us to this part. And remember, the kernel can also be defined in this way, where now you are, basically evaluating. This one is like evaluating the x, on this kernel anchored at xj. Therefore, you have this guy in here, right? See that? And then you put this back. What do you get? It is the fx itself. Okay. So what does this mean? This means that a evaluation of a transformation of a point into that reproducing kernel space through the h function phi is equivalent to just the inner product of this particular feature, okay, and also the function itself. That actually gives you an evaluation of fx. So this actually gives you a general kind of insight about what this Hilbert space is about. So when you actually do generic computation, what you do is to compute some evaluation in the original space, right? By plug in your value x into this f. F could be a arbitrary function. It could be the mean of the distribution, right? And could be some other transformation of the data. And we assume that very often this evaluation itself may not be that easy. But now with the RKHS space, this evaluation translates to an inner product, okay, between the two functions. Okay, this is a linear operation that is standard in that space and supported. And that's basically how you're going to get a saving down the road. Okay, so that's basically the reproducing property. You reproduce yourself by multiplying a dot product with a feature in the space. And because of that, now you can see this nice intuition under the SVM kernel. Every point in your original data set now correspond to a feature function in the RKHS space. Because when you want to evaluate this guy, whenever I want to evaluate a function over that, all I need to do is to now multiply this with that. Multiply with my function with this guy. Then I get a f of xi, right? So this is a one-to-one mapping of a original data point into a feature function. Okay. And so the insight here is that once you have such a explicit transformation or feature mapping from the original data to the Hilbert space, then you can do nonparametric or complex operations of the data just based on these linear operations in the Hilbert space. Get to that point? So now I'm going to talk about basically everything inside this space because there is a one-to-one mapping from here to the original data. My data is now gone. Okay. Okay, so now let's talk about how to embed a distribution. Okay, that backs to our story. We have this whole thing, which is complicated, and I have data points. Okay, and x1, 2, 3, and I'm going to now embed distribution in the Hilbert space. How should I do that? Well, analytically, you can see that the mean vector, okay, by definition, is the expectation of the transformed vector in here. By the way, this is implicit. Therefore, you actually don't know how the phi look like at this point, right? But it is a function. You can imagine this phi x to be some kind of a function, okay, anchored on x and taking whatever free argument. You can take that as the explicit form. And now I'm going to define the mean of that to be the expectation over this. And here you can have the explicit form in integration. Of course, in a finite sample, what does this translate to? Right? Become a summation, right? And so this is the definition of the mean. And I'm going to basically now show that this is a way to actually map the original distribution using this mean operation. Okay. And how does it do that? So what does mean map mean? So if this mean map is universal, first of all, this one can be evaluated based on this. Okay, and therefore I can go totally nonparametric to compute this mean. Here I haven't really taken any parametric assumptions about the original distribution, but here I'm taking a kind of implicit transformation of the data already into the Hilbert space. So we argue that this mean may be already quite expressive to represent distribution other than Gaussian. That's the first assumption. And then what is the, for example, here is an example I want to give to showcase you the utility of such a mapping. For example, suppose we are taking a random variable x, discrete, 1, 2, 3, 4. In fact, we saw this embedding before, in which happened to be also a RKHS mapping, which is that I have the first transformation like this, okay, the other point like this, the other one like this, I have this 4. Then my mean is basically the expectation of each of this mapped vector, right? Which actually gets us to this mean, which is the frequency of the events in every dimension, right? And that's already a interesting transformation. If you use the original expression in the data space, you get a mean that is pretty useless, right? You just mean over average over 1, 2, 3, 4. That is not very interesting. You basically lose the character of the distribution. But now through a transformation of the data into a more meaningful space, you get a mean that is, in this case, more useful. See that? So this is an explicit one where you know the transformation phi already, and you can make them do the thing you want. Now that you have a complex distribution that you actually don't know what that distribution could behave, you basically propose some kind of abstract transformation, okay, and hope for the best. You will see that, okay, when data gets mapped into even a higher dimensional space, good thing can happen. And my mean over there in that space will be something like this, will be more informative than the original mean in the data space. Okay? And also the transformation function in here is we have basically a library of kernel functions. We basically say that the transformation must be using the Mercer kernels, right? And that's basically what you do in SVM as well, choosing a RBF kernel or a polynomial kernel to do this transformation. All right. And so what is the utility for that? Again, you don't really explicitly represent the mu, because they are in the infinite dimensional space. You basically want it to be a vehicle to conduct useful operations on the original distribution, right? For example, I want to compute the expectation of any given function. That's a useful operation, right? And in the infinite dimensional, in the data space, this can be a non-trivial operation because you need to deal with the integration over f and all that, right? So now it translates to a dot product or inner product between this function and the other function, the min map. Min map itself is a function, okay? And how can we prove that? This is a simple proof, okay? By definition, the min map is the expectation over the mapping, okay? And then the randomness comes from x, which is not in f. I'm going to take it out, okay? Then I am going to, basically have e of x d. Right? I have that, right? And from this step to this step, what property we used? If you remember. The reproducing property, right? Because we are assuming that this f is a nice function in the RKHH space. Therefore, it always satisfies a reproducing property. I'm going to now evaluate, when I dot product this one with the base, I'm going to evaluate on that point itself. Therefore, the expectation of a function now translates to a very simple, inner product in the Hilbert space. Okay. So this is one operator, that you can use now already. It's representing a distribution in the form of its min operator, okay, in the Hilbert space. But that's basically for a univariate distribution. You have this argument which is x, which is a scalar, just one variable. What if we have two parameters, say x and y? How to represent a joint distribution, okay, in such a embedding? Okay, so without talking about the definition, I'm going to give you this property of that. If we actually have a operator, called the cross-variance operator, C of y and x, then this operator must have the following property. Okay, when I do linear operation, okay, in the RKHS space, in the form of f transformed by C, then inner product with G, I'm essentially computing the cross covariance between these two random functions. Okay. So that's basically what we call a cross covariance operator. Okay, it actually gets you a linear operation when you are computing the cross variance, originally using integration in the data space. And now, if f and g are both in Hilbert space, then this cross operator is essentially a embedding of the joint distribution f and x. Okay, we just call it an embedding because it realizes all the things we want to do with a two-parameter joint distribution. Okay, and this is again in the form of a operator, and therefore maybe an intuition you want to get is that you can view this as almost like a matrix. And if your f now is a function, then what this does is that you can have a function transformed with the C matrix, okay, and then you can multiply them with the G, and that gets you a number. and that number basically corresponds to the covariance between these two projections. Okay, and the reason we call this a embedding of the true distribution is just by a kind of a symbolic connection, because in discrete case, when you are describing the joint distribution of a two-parameter distribution, what do? You write a table, right, if it's discrete. And if it is infinite, what do? It is an infinite dimensional table, right? You basically have a matrix going x and y, and you put in all the numbers here. Basically, a pair of x and y gets assigned with a probability or density, right? And that's not explicitly expressible, and we use this function, okay, to denote this full distribution. Any questions so far? A little bit confusing. Feel free to clarify any inclarity here. Yes.
So how does like this embedding, let's say discrete variables, capture like the relationship between, let's say 0 and 1 is closer than 0 and 4?
Not yet. Okay. Yeah, I think that the earlier sentence was a bad example in motivating. That's not the only thing we want to do. There are many things. Even before we do that, the nonparametric assumption itself can be interesting. So here is sorry about that. Okay. Yeah. And the capturing which one is close to which is usually implicit in that design of the mapping function, and maybe we shouldn't really discuss that at this point to avoid losing the big picture. Yeah. Any other points? Are you clear with the dichotomy between a matrix algebraic view of finite dimensional distribution versus the operator view of an infinite dimensional distribution in a Hilbert space?
I see the connection in terms of the operation, but intuitively, what can you say? Is it sufficient to just compute moments of these functions in this high-dimensional space for whatever problems we want to do? Can you give some intuition about that?
There is never a thing called sufficiency, right? And what is argued here, again, by the way, nonparametric graph model is never about the intuitive. It is unintuitive in exchange for power. Okay, if you want power and intuition, there's no such free lunch. The intuitive thing is the Gaussian. You lose power. It's very intuitive. And here you say, well, Gaussian uses two parameters, okay, which is actually mapping. Gaussian is a mapping. You may say the mapping into two-dimensional space. Here I'm talking about you are mapping them to infinite dimensional space, including that mean and many other things we don't actually know. And then it becomes less intuitive, but we are hoping that this new representation is capturing something more than the Gaussian or other things, right? And what I want to emphasize here is that we talk about now functions and the operator instead of matrix and the vector. That's actually the most important difference. Okay, whenever we are in finite statistics, dimensional data, we have a vector, which basically gives you, a good, representation of what you are modeling. But here, when we say a function, it implicitly tells you it is an infinite thing, because it is continuous. You can plug in all the values in here and get a different outcome from the function, right? And you just imagine this function now, f, becomes a long thing, which is allowing to evaluate anything, any argument in that function, okay? And so without writing that, I put it as f. Then this c is an operator on this function, as if a matrix operating on a finite dimensional vector, right? Isn't that intuitive? So you have this finite thing f, and you get maybe a square rectangle matrix, and then you turn them into this, which is another vector, right? And now I have an infinite dimensional thing here. I call it f. Then I basically place a function here, an operator here, and that gets me to another function f, a g. And that's the counterpart. So this one roughly translates to this matrix operation. But because it is infinite dimensional, I don't really write it down in that explicit form. Okay, I call them just the operation as if I have this this f here. Clear about that? Okay, and you can view this as an infinite table. Basically, if you put a pair of x and y, there will be a value out of C from here. Okay, let's spend some more words on that. In fact, you can imagine now the definition, of the C is indeed representing that kind of structure. It is defined on the expectation of the outer product between two functions, two feature functions. One is, anchored on y. The other is anchored on x. These are the two functions. Okay, and what is the outer product between two functions? If you want to see a geographic or a geometric view, this is a transposed linear immediate vector. That is another one, and their product is a rectangular but infinite dimensional matrix. Okay, all right. So this kind of look like the uncentered covariance matrix, in the Hilbert space, and the counterpart of that is exactly like this in here, which deals with the finite dimensional vector. Okay, so we have now the cross-variance vector. And again, the cross-variance vector has this very useful function that when you want to compute out the covariance between two functions, you actually use a linear operation, okay, in the Hilbert space, rather than computing this directly. Just as if we originally evaluate a function in that space correspond to the inner product of the function with one of the features. Right. All right. So yeah, I apologize for the unintuitiveness of that, but that's the price you pay to get something more powerful. So now we are talking about this. It is actually the expectation of the outer products. Okay, that means you have multiple outer products. You have really a nonparametric way of representing this. Nonparametric means that every point is going to be corresponding to a function, okay, or a mapping in the Hilbert space. Like this is corresponding to one. Remember, we have this notion that there's a mapping between sample points to a feature function, right? So here we have one feature function from one point, the other feature function from the other data points, and so on. And then each of the pair between these two can generate an outer product. That's why you see here is an outer product, psi product phi 1, and 1 over 2, 2 over 1, 2 over 2, and so forth. And these are basically, nonparametric instances of the outer product. And then your goal is to define this operator, which is the mean of that. So what does it translate to? It translates to basically something in the middle. You do sum over, right? You basically sum, basically this one, C, Y, X, correspond to what? N over phi, Y, phi, X. Something like that. Okay? And again, you start to wonder, how I can really, express this. Again, in the whole business of nonparametric statistics or nonparametric linear algebra, I wrote this only symbolically. In your database, you never have that, okay? Because whenever they want to be used, they are never appearing in singleton. They will appear with a pair with the other one in the product space. Therefore, you are going to collapse them down into a kernel function. Right? That's the reproducing property of place rule. So all you remember down the road is the actual data points that you have in the data set, and then the kernel function you're going to use. And whenever there is an operation on that, you're going to, to use the kernel function. In other words, there is actually never a case you need to store the C or the mu. Okay, the C will only be used when it is actually working with the pi, or the f function will only be used when it is the inner product with the phi. That's the only time they get used. Therefore, you always see an inner product. Okay. All right. So again, here are just the examples of this so-called tensor product, because I'm showing you the two-dimensional case of two functions. It can be actually multiple dimensions and get them into higher tensor space. And you can see that these 3 data points in here and 2 data points in here gets you, instances of this many, and your goal is to sum them together. Each of them defines an outer product already. All right. So that's basically giving you a tensor product space. Okay, it's the two vector space, and that's where your covariance operator is defined. And now we can easily prove this expectation over 2 functions, the covariance of the cross covariance between the 2 functions correspond to these linear operations in the Hilbert space. And here is a simple proof, right? You just bring the definition of the C as the expected outer product of the 2 feature functions, and they apply to F, and by definition of the tensor of the outer product, you can now distribute the arguments in here, and 1 goes to this and 1 goes to here, and then due to reproducing property, this one gets itself and that one gets itself evaluated at x, y correspondingly. Okay. All right. So in a nutshell, once you define the reproducing kernel Hilbert space, everything become a inner product, okay, in that space. And then whenever you run into an inner product, you replace them with a kernel, and that completes the actual operation, that is defined on directly data points. And just for some technicality, I want to also talk briefly about this something called the autocovariance, which is the outer product of 2 feature functions themselves. Okay, and what is the utility of that? The utility of that is to generate this operator called the autocovariance operator for you to define the so-called conditional distributions. So now we already see P of x be embedded through a mean mapping, right? We also see P of x and y be embedded by a C of x and y, which is the covariance operation. So now we are asking, how can we do this? You want to give it a guess how this look like? It's never wrong to actually try the intuition symbolically from your usual space of chain rule or product rule, whatever, and then just replace blindly those matrix representation with the linear algebra, with the operator expression. If you have, for example, this P of x and y as a matrix, if you have the P of x as a matrix, as a vector, what do you do to get this part? Anybody know that? Obviously, this one is a table, right? In this case, it is a 2 argument, and you actually have a table which is a P of y given x, and maybe one row is x fixed at 1 value, okay, and then all the possibilities of y, and the other is x fixed at another value, and all the possibilities of x. This is a matrix. And I can tell you that this matrix corresponds to this other matrix P of x and y divided by P of x. And how do we express this division? It's actually in the form of an inverse matrix of a diagonalized P of x. Okay, just go back and convince yourself. We don't put a matrix vector here, because if I put a vector here, you collapse. You actually do a marginalization. You sum over all the x already, and then you get a marginal of y. But now you want to have a condition of y, a conditional distribution of y given x. Then what you do is to now divide every row in this matrix, in this joint probability matrix, every row by the marginal of x. Therefore, the best way to do that is to make a diagonal matrix, okay, whose diagonal are just the marginal of x. You put an inverse of that. That effectively allows you to divide every row here with the same number in here. Okay, so that's the linear algebraic operation. Again, if you are uncomfortable with this you need to go home. It's beyond this lecture, just to do some fancy linear algebraic operation. And without saying, now you can imagine the operator of y given x naturally should be what? Should be C of x and y, and C of x, this. Okay, so I'm going to have that. So we defined this autocovariance matrix really for the purpose of this. This almost looks like a marginal, okay, of one of the variables, but it is not a marginal expressed in the form of a mean transformation like a mu x, because we need to have a diagonal matrix, okay, for this kind of operation. Okay, and so yeah, that's it. So the intuition, I think I said it already. You can directly follow the intuition of the definition behind the conditional distribution. All right, so this is a new embedding. Now we learned 3 embeddings already. We have a embedding of the conditional operator. We have a conditional distribution. We have an embedding of the marginal, the joint distribution. And we have an embedding of a univariate marginal distribution, which is the mean embedding. Okay, and in here, again, the evaluation can be very, very interesting. Again, the evaluation of a conditional distribution using this operator is again a linear operation. So again, taking the intuition, we have this matrix of a P of a y given x. Right. So here it must be probably P of y given x equals to 1, and P of y given x equals to 0, something like that, right? And now computing a evaluation of this on a particular value of x, meaning that you are taking one of the row out, right? Not the other row. And this is basically an operation in here. Okay, you are going to now operate on a feature vector here. And remember, due to the reproducing property of the kernel, you are going to actually reproduce yourself in here, which actually gives you one row of the value. And yeah, so this is the slice operation I just wrote in here. So everything here is in a functional space rather than the matrix space. Here you'll see a more intuitive event that takes you a row out of a matrix and so on. Here, we no longer have a matrix that is finite dimensional. We are really having a function who, when necessary, will be expanded to an infinite dimensional. But what's really happening is just operators on that. So that's why you have all these symbolic expressions. All right, so with that, I think we achieved the goal of today's lecture. We introduced a number of basic concepts of defining marginal joint and conditional in the Hilbert space. And next time, we're going to now see how to make this kind of basic construction to work for our standard inference and learning problems. And again, remember that the good thing about the Gaussian is because they can rather easily support chain rules and marginalization rules by very clean closed form kind of expression. And we argue that in here, in our nonparametric space, we have the same flexibility. It's just to make explicit here. Here you have the summation rule, right? And here we almost have the same symbolic rule that evaluating on a mean function equal to the conditional times inner product with another mean transformation of the other arguments. And the chain rule is also here. So you can see here, I have the inner product rather than two operators in the form of a matrix, because here I need to marginalize out one thing. Therefore, a matrix times a vector. In here, I have a matrix times matrix to make sure that I'm still end up with a matrix, right? But here, the matrix here is the autocovariance of one random variable, which is actually a vector, but I make them diagonalized on the matrix to make sure that I don't lose any argument in my operation. Yeah. So hopefully you get used to this kind of very tricky algebraic way of manipulating the numbers. this whole field of nonparametric and the kernel graphical model is somehow not popular, exactly because all these very, very fuzzy, and unintuitive manipulations over vectors and matrix. But if you overcome that, you get some, hopefully, a nice utility out of it. Okay, next time we're going to prove what I said here, and also show you how to do Billy propagations, okay, using these type of models.